Welcome to today's discussion about high-performance cutting tools today with Kennametal. My name is John Einberger. I'm the product line manager for horizontal machining centers here at Makino, and we're coming to you today from our headquarters for North and South America in Mason, Ohio. I'd like to introduce Mr. Chad Hefflinger. Chad is Senior Application Engineer at Kennametal. Chad, can you tell us a little bit about your history and your position with Kennametal?
Sure, John. I started out in this industry in 1986 at a little company in White House, Ohio called Clapp and Haney Tool, and at that time they were making carbide brazed tools mainly. They decided to get into the PCD cutting tool market. It was brand new back then. I was one of the first few guys that we got hired in to start what we called the diamond business then, so I've been involved in it from that time in pretty much every aspect of the manufacturing, quoting, engineering, design. I was the plant manager up there for a while. We were bought out over the years by a couple different companies. Kennametal purchased us in 2008. I've been out in the field, mainly application side and sales, since the early 2000s, doing the application of the products. And so this is kind of what I know. I'm kind of a one-trick pony. I've always done PCD and also CBN cutting tools, because that's what we do there. So they're a bit of a niche cutting tool out in the market, but it's what I'm familiar with.
So we definitely have the right expert to talk to here today. Little bit of housekeeping before we get deep into the subject matter today. On the screen in front of you, one of the things we'd like to do is address questions that come up from the viewing audience real time at the end of today's formal presentation. I have circled the Q&A section. That's the area where you can put in questions. We'll review them as today's event goes on, and at the end we'll rejoin and take those questions and give you the answers. One last item, we have a poll question. We'd like to learn a little bit more about what you're using in your plant today. Very specifically, the poll question is pretty simple, yes, no question. Do you use PCD tooling in your machining processes right now? That gives us a little bit better feel when we look at these type of events. Are we hitting pertinent areas in the interest zone for the customers that are out there? So again, today's topic, high performance cutting tools with a focus specifically on PCD. So with that in mind, Chad, can you give us a bit of basic information, definition of PCD, things of that nature?
Sure. So PCD, stands for Polycrystalline Diamond. This is where the diamond bonds or crystals are bonded together to form a cutting material. It's pressed and sintered on a carbide substrate so that we can take that and utilize it to make it into a cutting tool. Yeah, so the composition of PCD is typically made from synthetic diamond powder that is pressed together. Very basically, it's about 1,000,000 pounds per square inch at 1,000 degrees centigrade, and you get what we call a PCD diamond segment at that point.
What applications, I know that we're talking about, the one that pops up on the screen right now, cutting tools, but Chad, are there other applications that PCD are used in outside of maybe even what the viewing audience is familiar with right now?
Yeah, there is. I mean, when you talk cutting tools, it's mainly non-ferrous materials, aluminum, copper, brass, plastics, CFRP. The bulk of what we see out there is the aluminums though, but they are also used in other applications. So the oil and gas industry, the big drill heads that they have to go for oil, there's large diamond segments that are attached to those. It's a little bit different than the materials that we use for cutting tools, but again, it is used in that application. And then also in wear parts, you'll see it in, we used to make some crank polishing tools where they had a lapping paper that would go through look like a shoe that had diamond wear plates on it because it was so abrasive. But you'll see it in those applications. A little more niche, but there are other applications out there. And then obviously abrasive as well. The grinding wheels that you see out there, those all have diamond impregnated into the wheels to do the grinding with.
Chad, are there still opportunities to provide educational materials that really talk about the operational aspects of PCD tooling out there?
Yes, there are. There's educational institutions out there today that really focus more on the polycrystalline or PCD diamond. Years ago, it wasn't as well known. I mean, it is much more known out in the industry today, but there are still applications. There's professional development out there. Applications like guys like myself, you get in this field, you start applying it, you'll learn about it. There's trade shows and conferences. In fact, we were just at the IMTS trade show. You'll see PCD focused in certain booths there. We had a section on it for sure in our booth. Online platforms, I mean, there's virtually nothing you can't go online and look up through Google or AI anymore, but that's another avenue that you can look into. And then the publications, trade show magazines, things like that, you'll see advertisements and knowledge in there about the products in those applications as well.
Still a lot of good examples out there in the trade show, or I'm sorry, in the publication realm of use case scenarios, things of that nature.
Yes.
So a lot of good information still available through platforms like that. Can you talk a bit more about how PCD inserts are manufactured?
Sure, John. So what you see there is that's actually the diamond puck or segments that we get in from our suppliers. The round disc you see in the center is the PCD. The black layer that you see on there is the actual diamond itself, or the polycrystalline diamond. It's centered together. Underneath is a carbide substrate layer, and that's basically there so that we can braze it on to whatever cutting tool that we want to make. You see the segments below. We basically take that round disc. It's between 58 and 76 millimeters, depending on the type of material we're getting. And we cut it into the near net shapes that you see down at the bottom with the wire EDM machine. And then from there, we can braze it onto whatever cutting tool we're looking to utilize. It could be something as simple as a CNGA insert that we're going to put a diamond on the corner of, or it could be a very elaborate multi-fluted diamond reamer for a spool bore, or maybe a spark plug housing on an engine. And that's where the base starts. And PCD is unique. Diamond is the hardest substance known to mankind. When you grind diamond, we're using a diamond wheel to grind a diamond. I used to tell people it's a bit like cutting a 2x4 in half with a 1x4. Very difficult to grind. We also use wire EDMs and laser machines. Laser machines are the newest technology. That's probably been the largest development in PCD manufacturing. In my time in it, at least, we can be very accurate and get very keen cutting edges with the laser machines. And then inside of that, that's some of the products we're talking about, the hole making products at least. You can see some examples of some drills, countersinking tools, straight reamers, and then different combination tools that we can do: tree panning, milling, boring, and drilling tools, just about anything that you can imagine put to a print. We can braze a diamond on the corner and make a cutting tool out of it.
When you look at a tool like this, Chad, something that's customized, something that's special, are you typically going to be using inserts on that, or is it going to be more of a monoblock style approach?
Great question. Typically anymore what we see is the monoblock style approach. The speeds that we're machining at today, some of the lengths that we're reaching out to, and again, as I mentioned earlier, diamond is very hard, but it is very fragile, so rigidity is key for it. And the tolerancing that we're holding on these tools now really doesn't allow inserted on some of these. They're brazed construction. It's the most rigid tool we can make. It allows us to design in the flutes how we want them to be, and then it's just a more rigid setup all the way around.
So from the standpoint of using carbide as maybe the standard, if you will, can we talk about some of the advantages that the PCD is going to have over carbide in the applications that it's really well suited for?
Sure. So when we look at some of the characteristics of PCD, it's the maximum hardness. I talked about diamond being the hardest substance known to mankind, which gives it tremendous abrasion resistance. So in any non-ferrous applications, we apply these diamonds. It gives us, and you can see the laundry list of advantages there. We can get a longer tool life. It can run at much higher velocity speeds and feeds in non-ferrous materials than we can with carbide. And because it is hard, and it's roughly 50 times harder than carbide, let's say on a Knoop scale, we can see typically a minimum of 10 times tool life over carbide, which is generally the minimum you have to see, because PCD costs about 10 times what carbide does. But it's not uncommon to see up to 50 times tool life. We've had PCD tools in production applications go 100,000 holes on specific reamed holes in an engine block, let's say. So that's the advantages of it. Because it lasts so much longer, it's sharper, it's harder, burr formation's less, finishes are better. I mean, like I said, there's a whole list of advantages for the PCD over carbide.
One of the things that we always face in the industry today is lack of availability of people, manpower, resources. So really having a tool that goes into the machine, being able to run that tool for a very long amount of time before you have to service it in any way, shape, or form certainly is one of the steps towards addressing that manpower shortage.
Absolutely, we talk about PCD and non-ferrous applications. The largest application for PCD in the Americas anyways is the automotive industry. There's just no one else producing millions and millions of cast aluminum parts that have a medium to high silicon content in them. And when you're producing that many parts, as you mentioned, that's where you can justify making a combination tool with multiple diamonds on it. It's a very expensive tool, but it can do multiple features at one time very quickly and last for months in the machine.
So from the standpoint, just to summarize everything, maximizing productivity, overall, even though, as you say, the cost up front is more, the overall economy certainly is beneficial.
Better. Yep.
All right, Chad, can you expand on both the costs and the benefits? I know you touched on it in the last segment just a little bit, but if we can look at a little bit more use case scenario, can we expand upon that a little bit?
Yeah, so we did talk about a little earlier, and you see here there's a straight tool cost wise. You have your carbide tool on the left and the PCD on the right. And again, it generally depends on the type of tool, but it can be up to 10 times as much as the cost of carbide. So there's a sticker shock of it on the initial, but when you, as I mentioned earlier, when you're running these in the applications, it's not uncommon to get 10 to 50 times tool life PCD over carbide in these applications. And then in the speed we've touched on earlier, we can run these at probably 10 times the speed that we can run a carbide tool in most applications, so you get better throughput with the tools. And the overall, when you look at those three things, when you look at the end CPU on PCD versus carbide cost per unit, it's much lower than the carbide tool, even though the initial sticker shock is high. And what I always tell people is it has to, the diamonds have to justify themselves because they're expensive. You know, if we can't make that kind of tool life, you can't afford to buy them.
So how do the characteristics of PCD tooling relate to the cutting parameters specifically?
Yeah, so see a lot of milling in the applications that we run, and when we talk milling, generally we can run between 1,000 meters and 4,000 meters a minute speed-wise, and these are aluminum parameters that I'm giving you, and this is, the range there is based on the silicon content and how maybe abrasive the material is, or if we're cubing, sometimes there's green sand castings, is a lot of scale on the outside. Sometimes we'll run a little slower in that range to help out with tool life there, but that's the kind of range we can run, and it's a pretty big range, honestly.
One of the things that comes to mind from the standpoint of cubing, in those instances where we still see customers use lost foam casting, any special considerations from the standpoint of that initial milling pass relative to the product that comes out from a lost foam process?
Yeah, in fact, I was involved in some lost foam process machining several years ago with General Motors, and the lost foam process, it leaves a scale on the outside of that material there because there's a ceramic that gets impregnated in there, and it becomes very difficult to machine in the cubing sense. So in the one that I was involved in, we had to run a really low speed to get through that. The ceramic particles in the scale was microchipping the diamond. So we slowed the speed down and was able to get through it there. And that's where the range can help you. You can kind of dial that speed and feed into your application or machine or fixturing, whatever the case may be.
So one thing to keep in mind is not necessarily one set of parameters fits every application. You do have to take kind of that starting point scenario into consideration when picking those cut parameters.
Yeah, and these are general parameters, yep. For drilling, we're in the 350 to 700 meter range. Countersinking, very similar. We do a lot of tools that are drilling and countersinking or reaming and countersinking. So they're all in a similar range. And the reason that they don't run at the higher speeds that we see in milling is because in all those instances, whether we're drilling, countersinking, or reaming, those tools all have radial margins on the diameters. And because we're basically burnishing that hole down, we can't run at the elevated levels that we can, or we'll actually burn the part up going in. But those are the ranges that we run in. And it's typically not an issue in the world we live in with the drilling, countersinking, and reaming, because they're typically, I would say 80% of the holes we produce are 14 millimeters or smaller. So you have to, even if you have high RPM machines, if you have an 8 millimeter, say, diameter tool, that's just for easy math, even if you're running that at 10,000 RPM, you're only running at about 300 meters a minute speed. So it performs well in those parameters for it.
From a feed rate standpoint, how does that pertain to this discussion?
Yeah, and again, it's by application to some degree. These are general parameters, but from about 0.1 per tooth up to about 0.25 a tooth is where we like to run these. And for me, particularly in the milling side, I'm a feed it kind of guy. I also time and cut guy, that tool life on and on. Generally, the failure mode in milling, or what we want it to get to, is burr formation at end of life. And what I typically see is that people think PCD and they think fast, so they run high speed, but they think it's fragile and they need to run low feed. And that's somewhat the death knell of it. That's how to produce a burr very quickly using PCD. So the higher chip load when we're exiting the part tends to cut cleaner coming off the edge, and we can run longer without producing that burr.
So the thing to keep in mind, the feed per tooth might be equivalent between the carbide and the PCD, but the overall feed rate in the form of millimeters per minute or inches per minute is going to match what the differential is on the speed. We have seen cases where customers have made a move, for instance, from carbide to PCD, changed the RPM in the spindle, didn't change the millimeters per minute, couldn't understand why it wasn't any faster. Yeah. Kind of interesting stories like that.
No, and I can remember when we first developed one of our early milling cutters. This would have been back in the probably early 90s, and I was on the phone talking to an engineer, and he just got a brand new CNC machine, because back then a lot of the machines were dials and transfer lines, and it had 10,000 RPM capability on it, and there was not a lot of machines like that. And we had a 4-inch cutter with 12 teeth in it, and I said, well, you can run it at 6,000 RPM, 600 inches a minute. And he was shocked, by that kind of speed, but that's just how the math works out. As you get the RPM up, like I say, the feed rate goes
Yep.
up.
So a couple of points also, Chad, around the overall thinking about things as an overall system with that cut process and all the parts that go into it.
Yep, and there's, like I said, general parameters, but there's cases where, because of a thin-walled section of a part, we can't run the same parameters, or there's always the exceptions to it. So yeah, it really depends on the part, the fixturing, the machine, the whole package when you're looking at it.
Yeah, that overall system dynamic really comes into play. So Chad, can we look specifically at the milling parameters when using PCD tooling? Get away from the hole making here for just a moment, but focus on that milling part of the overall process. So,
and I've talked about this, PCD can operate in a wide range of speed. We can, run down as low as 300 meters a minute up to, say, 4,900 meters a minute, depending on the application. Very low silicon aluminum content, say extruded aluminum, 6061, 70 series aluminums. The less silicon, the faster you can run it, because there's nothing really abrasive in the material. The other end of that is like an A390 material, where you've got 16-17% silicon content. In those, you're going to need to be into that 300 to 500 meter range to get your ultimate tool life. So for me, in most aluminums that we see in the automotive, the 12 to 1800 meters a minute is, for me, the optimum for overall tool life. Now, if overall tool life is the most important factor, then that's where we want to run it at. If throughput is the absolute factor, we can run it faster than that. Like I said, we can run up there. You're going to trade off a little tool life, but maybe the throughput is what we're looking for in that.
changing the topic a little bit, still with milling, but looking at considerations around feed rate.
So in milling, we can, the lowest I like to run is around 0.7076 a tooth. And those are some very unique applications. We can actually do bimetal milling with PCD. And when I say bimetal milling, these are your aluminum engine blocks with cast iron sleeves in them. Even though there's iron in the sleeves and it's ferrous material that technically PCD shouldn't cut it, it's the heat that causes the issue with the ferrous metal. So if we can keep the heat out of it, and we run about 300 meters a minute in a bimetal application. And because that diamond's hitting the iron, we'll run a little bit lower feed rate in those instances. But generally speaking, I like to run up around 0.2 a tooth when we're milling. That gives us the best exit chip for burr formation. So typically I want to get you to where your tool life, end of tool life, is a burr formation. We shouldn't be pulling a mill for finish or flatness. If we are, we need to address those issues and get it to burr. And then once we get it to burrs, how do we prolong that longer? And the thicker chip coming off the edge helps with that burr reduction.
So maybe a little bit different way to think about it as you're using this kind of tooling in your shop, in your application. That really is kind of an interesting discussion around what that end of life indicator is. All right, so what does PCD tooling and its use mean in terms of surface finish capabilities?
So you talk a little bit about some of the hole finishing. I mentioned this earlier, that because there's radial margins, we're somewhat burnishing these holes. You can see RAs down into the 0.1 to 0.3 range on reamed holes. The RZ 0.5 to 1.5. The spot face is a little higher because it's not typically the front cutting edge of that counterbore we're doing the bottom is an up sharp edge, so we can't get quite as good a burnish finish there, but there's still fantastic finishes that we can get with the PCD because it's sharp.
So how do various PCD grades relate to the workpiece properties? I know you talked a lot about the silicon. Are there differences from the standpoint of that substrate, not the substrate I should say, but of the diamond itself from the standpoint of grain size relative to working with different silicon contents?
Yeah, so I mean, and I'll say this, there really isn't different grades of diamond. There's one grade, it's diamond. Now inside of that, we can make different size grains, and they can make them different shapes and orient them differently for the applications. And I would say in 70 to 80% of the applications that are out there, you could run any grade, and it's basically coarse, medium, and fine, these particles we can get. You could probably run any of those grades and not see a measurable difference in the outcome of the tool life. But in very specific applications, if it's very abrasive, or if it's weak, or we're seeing microchipping, those are two of the basically failure modes we see, is abrasive wear or microchipping. If we're seeing abrasive wear, the coarser grain materials have a little bit of an advantage in the abrasive wear side of it. I also mentioned the bimetal milling. It's kind of a niche, but that's another area where we would run our coarse grain material, because the larger diamond crystals actually, even though the size of them is 25 to 30 microns, the larger crystal disperses heat better in those applications. So it is an advantage in the bimetal. In other milling applications, typically the failure mode in milling is because it's interrupted by nature, is microchipping. And the finer grain materials are a little better against microchipping. So generally I'll lead with those in milling, unless I know it's a very abrasive application, say a lost foam casting or a green sand casting that you're cubing, it's got a lot of scale on the outside. That's where we may use the coarser grain. And in our world, the Kennametal world, it's particularly in the milling, these are the two grades that we discuss, and it's the 1425 is our coarse grain multimodal diamond grade, which gives us very good abrasion wear resistance. And then our 1400 grade is a fine grain, sub-micron grain material that again is a little better chip resistance. And we'll show some pictures and slides of that going forward a little bit. Yeah, so we talk about abrasion resistance, and it's very difficult to see in that picture, but there's just a slight wear on the very top cutting edge where it's rounded on there a little bit. And when we're looking at failure mode analysis, that is classic abrasive wear. The edge started around. And if that's what you're seeing, 1425 is the right grade. It's a little better abrasion resistance because of the larger crystal sizes in it. And then I talked about the microchipping or the chipping resistance of our KD 1400 grade because it's a fine grain material. I hate to say it doesn't really give the diamond toughness because diamond is not tough, but it makes it a little more chip resistant. And when you see the picture there, those microchips along the edge, when you see that, that is definitely tailor-made microchipping, and that's kind of where we would see on a lot of milling applications. You can get that because sometimes long reach, parts that are maybe not well supported or things like that, that's where you can get that microchipping.
So let's close out today's discussion from the standpoint of handling these tools. Decision was made. We're implementing PCD tooling. What are some of the things for every shop to think about in terms of best practices from the standpoint of handling?
Yeah, so non-contact gauging is what we're looking for. We don't see a lot of that in today's world. When PCD was very new, when I started this 38 years ago, we had to really be conscious, tell people how to handle this stuff. Pretty much everybody has some type of vision system now that they can measure these tools. So that's critical. The other critical piece is just the storage and handling of these. Because diamond is very expensive, particularly on some of the tools we're picturing there, they are reworkable. And if you don't take care of them, you can lose the rework of the tool, and it's costly if you have to buy new every time. So just keeping them separated in drawers and keeping them boxed up well, and you can return them, you can get multiple uses out of the tools in some cases for the rework side.
So I'm going to close out with a question to the audience out here. Chad, thank you very much. First and foremost, Thank you very much for the discussion. But a closeout question, if this is of value to you, are there other tooling related discussions that you would like us to have? If you would, once again, use that Q&A section in the screen that's in front of you right now. Let us know other ideas that you've got that we can research, that we can bring in the factory experts, that we can have more of these discussions in the future. I want to thank everybody for tuning in today. Once again, this was High Performance Cutting Tools. Chad, thank you very much for bringing a lot of wisdom to the discussion. Normally we would go to a live Q&A at this point in time in the EC event, but due to logistical constraints, we're going to take your questions and answer them after the fact off air. Thank you again for joining us, and we'll talk with you again soon.